for part A, wants a graph with these data points. So I'll make my x-axis time in seconds. I'll make my y-axis force in newtons. I'm doing this because force is dependent on time. So therefore, time being my explanatory variable and force being the dependent, the reaction, the whatever variable, the one that responds to time, it would make sense to graph it like this. So 0, 1, 2, 3, 4, 5, right? And then for force, 20, 40, 60, 80, 100. So let's graph the data points. At 0 times equals 0 seconds, the force is 100 newtons. At 1 second, the force is 80 newtons. Let's make that neater. At 2 seconds, force is 60 newtons. Sorry if I sound a little bad, I'm sick. At 3 seconds, force is 40 newtons. 4 seconds, force is 20 newtons. 5 seconds, force is 0 newtons. And let's draw the best fit line. Do all the data points. Seems linear, actually. Alright, so there you have it, the graph. Now, using the information from the graph, determine the expression for f of t as a function of time. Well, we can see right here, this looks really linear. So we can use y equals mx plus speed. Linear function, right? Where y is now force, but as a function of time, is equal to whatever the slope is. So rise over run, down 20 over 1. So negative 20 t, because that's the new variable. And then plus wherever the y-intercept is, which would be 100. Plus 100. So this function right here, the linear function, can be used for our b, for part b. So let's bring that. Actually, I have the whole thing on here, so I just rewrite it. T equals negative 20 t plus 100. To clarify again, this would be in newtons, and time is in seconds. Derive an expression for acceleration of the cart as a function of time. Well, we have the force. What we have to do, divide it by mass. And where's the mass? Right here. Cart of mass 5 kilograms. So, first off, I know that sigma f is equal to mass times accel. And our sigma f would be this function right here, this f of time. So f as a force as a function of time. So let's bring that down. Negative 20, let's make it right here really smaller, t, plus 100, because that's my f of t I found earlier, negative 20t plus 100. Is equal to mass times acceleration. Well, since this is a function of time, once I divide this constant mass, the acceleration naturally has to take on becoming a function of time. So I'm going to do that. Divide by mass, which cancels it out on this side. And we know the mass is equal to 5 kilograms. So I just need to divide here. A of t would be equal to negative 4t, and then plus 100 over 5 would be plus 20. So there you have it, A of t, acceleration as a function of time. Now I need to sketch the acceleration as a function of time graph on the grid below, right? So once again, I have acceleration here. This acceleration, which is in meters per second squared, is again in response to the explanatory variable, time, in seconds. Therefore, I would graph time as my x-axis again, and acceleration as my y-axis. Makes sense. So once again, 0 seconds, 1, 2, 3, 4, 5 seconds. Once again, same scaling. move this over. And then move my 100 up. So yeah, this is my y-axis, my x-axis. Now, where did my marker go? Okay, there it is. Now I need to graph the points. Well, a at 0 is going to be just 20. Makes sense because that's my y-intercept. A at 1, it's going to be negative 4 plus 20, so 16. Oh, so really it doesn't make sense to scale it like this. Let's rescale it actually. Because I know it's going to be decreasing because of the slope is negative 4. So really the maximum is 20 and it's decreasing by 4s. So it makes sense to make my axis decrease by intervals of 4. So 20 actually. 16, 12, 8, and 4. And now, let's graph the proper points. Y-intercept 20, so there's my first point. 20 at time equals 0. Now, negative 4 times 1. Negative 4 plus 20, 20 minus 4 is 16. 20 minus 8, because negative 4 times 2 is 12. 20 minus 3, minus 4 times 3, 20 minus 12 is 8. 20 minus 4 times 4, 20 minus 16 is simply 4. And 20 minus 4 times 5, 20 minus 20 is, there you go, 0. So let's draw the best fit line. Looks like a decreasing linear function. And there you have it, acceleration with respect to time. Now, what information can you extract from acceleration versus time graph? Well, you see here, we have the slope. We can find the slope of this graph fairly easily, right? And you see that acceleration as a function of time, if acceleration isn't constant as a function of time, if you were to differentiate that, that will get you jerk, right? And depending on what it is, jerk could be a function of time or jerk could just be constant. In this case, since you only have one variable here, it's only a linear function of t. If you were to get the derivative of this, it would be a constant, so I'm just going to write j for jerk, right? So you see, if we were to find the slope of this, which by the slope of that, I mean the change of a, dA, because that's delta basically, in respect to change of t, dA dt is equal to a prime of t, and that's simply going to be jerk. So with this graph, you can extract jerk, because the jerk as a constant, because we have the slope of the acceleration graph, which we could easily find. So from this acceleration versus time graph, we were to get the slope, we can extract jerk. But really, we can also take the area and extract the change in velocity. Because if we take the area under the curve, that's integrating a of t with respect to time. And integrating a of t with respect to time would get me v of t. But since I have bounds here from 0 to 5, if I take the area from 0 to 5, right, that would get me the change of velocity from 0 to 5. So that would translate to v of 5 minus v of 0. So really, we have that. Since I don't see an initial speed, I believe you'd have to assume it to be 0 if you wanted velocity as a function of time. Otherwise, you would not be able to find that. But, just for sake of derivation, if I were to assuming vi is equal to 0, then I could find velocity as a function of time too, by integrating at dt, and that gets me v of t. So let's do that. A of t, integrate that, it's going to be negative 4 t squared over 2, because, add 1 to the exponent, divide by that exponent, and that simplifies to negative 2 t squared. And then the constant, I just need to add t to that, because if I were to differentiate that, again, that would get me the 20, which I'm integrating. So, that's how integrals work. They're the antiderivative. So then, it's going to be plus 20 t. Hey, Mr. Luong, this isn't a true statement right here. I just wrote this because I was simplifying. I set it equal to what it simplifies to, and then I add the 20t from the integration above. Thank you. And then, regardless, there's going to be a plus c. And this plus c I cannot find with this information given. But, given I assume vi is equal to 0, then yes, I can find plus c, because plus c would just be 0. So, theoretically, if you were to assume, because the information isn't given, and Mr. Luong told us to assume that vi equals 0 unless otherwise stated, then yes, this would be the velocity function, v of t. Velocity with respect to time. Another piece of information I could extract, assuming there's... No, not assuming. This is what the acceleration is at the start. Given the fact that force is 100 newtons at the start, I can really just find the change of acceleration between two given times by just doing a at my final point minus a at my initial time. So a at f minus ai. So then, really, a at 4 minus a at 0, that gets me the change of acceleration to be negative 16 meters per second squared. So, yes, with this graph, I can find acceleration at any given time, and I can find the change between 2 points. Which I could do like, let's say, for example, acceleration at 3 minus acceleration at 0, and that gets me a change of 8 minus 20, negative 12 meters per second squared. So, hey Mr. Luong, also from this graph we can observe and extract the information that velocity is increasing because acceleration is positive in this 5-second interval. We can find the change in velocity because you can take the area under the graph, and you can also find the force at any given time in this 5-second interval because we have the accelerations for that, and force is equal to mass times accel. That's all the information you can extract from this graph. And the F, G, H, I, J, K, 2. Looks like you can call me the telepath because it wants an expression for the instantaneous velocity v of t as a function of time. Well, looks like I found it assuming vi equals 0 because no other information is given. So I can just rewrite that down here. V of t is equal to negative 2c squared plus 20t. And this would be in meters per second. So I'm going to just clarify that. Do I need to clarify any other units? I don't think so. Well, here, jerk is meters per second cubed now. Not meters per second squared anymore. And the reasoning for that is because this is meter per second squared, and you're dividing it by seconds again, so then you bring those seconds up, and it's meters per second cubed. Yeah. Acceleration is meters per second squared. I'm pretty sure I clarified that, yeah. So yeah, let's move on. Using the information can be extracted to determine v at t equals 5 seconds. So you see, we assume that v at, let's say, 0 is, 0. So then really I just take the area under this, or I can really just plug this in, v at 5. So, no, I cannot use the information that can be extracted from a of t in part E. So I must take the area under the curve. It's a triangle, right? So I can do 1/2 base times height. Well, 1/2 of the base times height. Well, what's the base? 5. What's the height? 20. 5 times 20. Half of that is equal to 50. So that shows me that the change in velocity over 0 to 5 is going to be equal to 50 meters per second. And because it's a vector, I need that positive sign. And I wrote that incorrectly. Let's go fix it. As Mr. Luong would famously write in his damn stupid puzzle. I mean, no, not stupid. I love you. Puzzles. T equals 0 to 5. Right? Well, actually, I don't know if he'd write t, but you get the idea. T equals 0 to 5. Right? It's plus 50 meters per second. Well, I know vi is equal to 0. So, vi plus the change, delta v, from 0 to 5, would basically get me v at 5. which is just going to be flat out 50 meters per second. Oh yeah, he would write the t equals so v at t equals 5 is simply equal to 50 meters per second in the positive direction. Let's move on. Using the v of t function, determine the value for v of t equals 5. Oh, this function right here. Well, okay, let's try it. V of 5 using said function would be equal to negative 2 times 5 squared plus 20 times 5. Well, that's going to be 5 squared, 25, negative 2 times 25, negative 50, plus 100, negative 50 plus 100, it's going to be equal to 50, again, meters per second, and it's going to be positive. So, yeah, it checks out. They agree with each other. Happy, 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 happy. Derive an expression for position x of t as a function of time. Well, it's time to bring out the old calculus. So if I integrate v of t with respect to time, that would get me x of t. So I have to integrate this stinking function. Let's go do that. Not complaining because I need every point I can get on this puzzle. As Mr. Luong, you know my situation. So, let's integrate. Integrate v of t, which I will just bring down, negative 2 t squared plus 20t with respect to time is equal to x of t. Well, let's integrate it. Add 1 to the exponent, divide by that exponent. Negative 2t cubed, let's make this smaller, over 3. Plus, again, add 1 to the exponent, divide by that exponent, 20t squared, over 2, which I'm just going to simplify instantly here, to 10. Because 20 divided by 2 is 10. And seems like that's it. Nope, plus c. Now, let's look above. Did they give me any information? Hold on, let's check. I'm going to cut this part out. Seems that no information was given for the initial position, so I would assume it to be 0, and since I assume initial position is 0, x of 0 equals 0, 0, 0, so c is also equal to 0. So it seems like this is my position function. And yeah, position as a function of time. And let's simplify negative 2 over 3 to be just negative 0.666. So negative 0.66. And this is in meters. Meters. Whew. Let's graph this damn function now. This is an interesting function where I will put my calculator to get the points that I want. But in order to, first, again, let's clarify. This is the explanatory variable, and this is dependent on that. So this is why I chose my x and y axis to be such. And now, again, like always, just get the time 1, 2, 3, 4, 5 seconds, respecting the whole graph. Ooh, wait. Oh, I forgot 0. funny. 0, 1, 2, 3, 4, 5. And now, really, how would I figure out what I should label my axis? Well, it's best to look at the points first, because I don't want to over-label, under-label. I want to fill up that sexy graph as much as I can. I think 200 would be a pretty nice number, wouldn't it? Well, actually, I could also divide 180 by 5 to get increments of 36. So let's do that. 36. 72. One away. 144. And 180. Whew. What an interesting axis. Now let's graph. At 0 seconds, position is 0 meters. That's what we assumed. Makes sense. At 1 second, position is 9.34. So 36 divided by 4 is like around 9, so it's 1, 2, 3, 4, 5, so it's, let's say that like around here would suffice. 2 is going to be 34.72, so just a little bit under 36. And 3, 72.18, so just a little bit above 72. We have 4, 117, so 8, 36 divided by 4 is 9, so 117, 117 minus 9 is 108, so I think I could say 1/4 up, so like around here. And then the last one, y at 5, well, x at 5 is 167.5, so just a little bit under 180. Once again, I can split these up into 9s. 180 minus 9 would be about 171. So if this is a 4th, then it's a little bit under that 4th. So there. And let's graph that function. Looks like it curves. So they want these 5, 1, 2, 3, 4, 5 lines, right? So I'm going to color code it for the sake of your eyes. Nice purple. A nice baby blue. I don't know, scab, diarrhea, and forest green. So those are the colors of the lines. So, pink. Instantaneous velocity at t equals 2. Well, we know that the velocity, right, it's going to be the change in position over change in time. And you know what gives you that? The slope of this position over time graph. Because that's going to be rise or run position over time. Well, if we want it instantly at 2 seconds, we really just need the slope at 2 seconds. So this pink line will show you that. Slope at 2 seconds. So that line represents the instantaneous velocity. Now, draw a line that represents the average speed between 0 and 1. Well, let's do that. Between 0 and 1, we want a line that represents the average speed. So let's get this baby blue color. 0 to 1, right? It's going to be the slope of like the secant line, because it can be the change in position over this 1 second interval, right? So it's going to be boop. And now 0 to 2, the average speed from 0 to 2. Again, it's going to be a similar idea from 0 to 1, right? But it's going to be the slope between 0 and 2, because, you know, it's just going to be the slope of the secant line. And it's the slope of the secant line because it's the average speed. It's going to be the change in distance over that change in time. So it's going to be that slope we get from this giant rise over this giant run. That's why I draw the line between those 2 points, because it's the giant rise from 0 to 2 over the giant run. Diarrhea color, 0 to 3. Well, 3's right there, so 0 to 3, giant rise over run. It's just slopes. Distance over time, average speed. Again, 0 to 4, average speed. Change in position, distance. Ooh, that's a bad line. Distance. Ah! Distance over time. Distance over time. So there you have it. Now we're here. This wants me to explain what happens to the average speed of the car during each second, right? Well, first off, let's look at this acceleration graph real quick. You see that this acceleration is always positive, right? Meaning velocity is always increasing. But we know that velocity starts at 0, because that's what we're assuming. So if we assume that velocity starts at 0, and velocity is always increasing, that means we can safely say that velocity is always positive. And since velocity is always positive, we know this position function, well, always positive in this time frame we're observing, we know this position function, right, is also going to be increasing in this observed time frame. And because position is increasing, that means for each second, you're going to travel more distance. Because from 0 to 1, you travel, let's say, this much distance, a set amount of distance. But from 1 to 2, since velocity is increasing, and that means velocity is present, and that means position is increasing, that means you're not going to travel the same distance you did from 0 to 1 for 1 to 2. You're going to travel more for 1 to 2. So then since I'm traveling more for 1 to 2, and the same for 0 to 1, right? Then if I do that value for 0 to 1, plus the extra I've traveled from 1 to 2, but I divide it by the same 1 second here, and the 1 second here, then average speed is going to be more. Same logic here. Position's increasing. I divide by the same, 1 second, 1 second, 1 second. It's going to be the same as 0 to 2, except here I'm traveling more per second. Here I'm traveling more distance per second. More distance per second. So really, the average speed is going to be increasing because over time, right, each second will take on more distance. It's going to travel more distance. And because it travels more distance and average speed is distance over time, the average speed is going to increase by a per second basis. And then they want the average between 1 and 3. Well, the average between 1 and 3. It's just gonna integrate velocity. And then over that time frame, 3, because this change in position, displacement, from 1 to 3, and this would actually be 3 minus 1, which is equal to 2 seconds at the bottom. So I can omit this. So yeah, that would get me the change of displacement over time, change of time. That gets me 31.33 meters per second. Since the vector, positive.